Hello again. I have a busy day. You have a busy day. We all have a busy day. There's lots of math to do here. I think we're starting the second half of the course. And one thing that happens when we start the second half of the course is, unsurprisingly, the mathematics gets more modern and therefore more involved. And we've probably seen the last peaceful day that we will. I want to write something, then look back at some materials to show you. So anyway, let's get going. Remember, we looked at Kayami solving the cubic. And when Kayami solved the cubic, it was like this, but I want to call your attention to a couple of things. The thing I want to call your attention most to is right here. So Kayami was working with side lengths, and this was an unknown side length. This was a side length. B was a side length. So that B squared X was that whole quantity there. The reason Kayami was doing that was because he wanted everything to be three-dimensional. And you might say, but this, and the answer is, if you look carefully at Kayami's work, this is actually not one length, but B squared times another length. So that is also three-dimensional. For Kayami, it was very important that all of the quantities were three-dimensional. This is something that didn't happen when we looked at Cardano and Ferrari and everyone else who was solving the cubic. That Viet, who is our first person to talk about today, working in 1591, he does want the quantities to all be the same dimensions. He is careful in this way that we tend not to be. So that being said, that's my introduction to let's look at Viet's work. So that got us going. Here's our stuff for today. Let's make it a little bigger for your sake. So here is Viet. There he is. Woohoo. And here is some of his work on algebra. And some of this we will skim over. Some of it we'll pay more attention to in different ways. The first thing is just this here is just kind of what he's going to mean by algebra. He refers to it by this curious name as the zetetic art, which is interesting, and I don't know anything more about that. So fine, I guess. And then he has some propositions from Euclid, which are kind of boring. Then he has here this insistence that we just talked about with respect to Khayyam. This is homogeneous quantities must be compared to homogeneous quantities. He is insistent that we deal with cubes separately from everything else, linear terms separately from everything else, and not combine them. He then has some nice rules of algebra. So chapter 4 are some rules of algebra. The first rule is really amounts to combine like terms. Okay, so we can fittingly add things that are homogeneous magnitudes. All right, that's fine. There's some talk of subtraction. The bold-faced things here are not quotes. So after Viet talks about subtraction, he also says we can subtract squares as long as A is larger than B. And there's this rule that Viet talks about not using this notation, which is this distributing the minus sign here, which is kind of a nice thing, I guess. Then Rule 3 is how to multiply really monomials. We saw Shukei talking about that. And that's okay as far as things go. And rule 4 is dividing. No, not dividing. It says it's dividing, but it really isn't. It's really how to add and multiply fractions. Notice there's this attention to what dimension everything is. So b plane divided by a, or b cubed divided by a plane. He's very attentive to what dimensions things are. This is, as I mentioned, closer to Viet, and Suzuki talks about this also. It's as if Viet is taking a step backwards to Kayami in this way. He also talks about how to add fractions. Notice the word in is used for multiplication, but they are using plus signs, and how to multiply a fraction by at least a number. All right, well, that's moderately interesting. There's something interesting that is noteworthy here in chapter 5. And it's not in the actual text, which is sad, but it is in the translation, or at least the commentary. So step 5, and the text is omitted, which is really sad because I'd really love to see how Viet said this. But Viet has this rule which says he's denoting unknowns by vowels and given magnitudes by consonants. You might think, wait, what do you mean if they're given? What's the difference between unknowns and givens? We do this a lot, actually. In fact, I was doing it right up here. You and I tend to denote unknowns by letters at the end of the alphabet, and given magnitudes, or parameters, we would call them, by consonants not consonants, but letters from the beginning of the alphabet. Notice I have X's here and A's, B's, C's, and D's for the parameters. Viet has a different assumption, but he does now have a distinction between parameters and variables. For him, the variables are the vowels, which is interesting because you somewhat limit yourself for how many you can have, but okay. And the given quantities are consonants. We will see this again soon when we talk about Fermat, which is who we're talking about next. So we will definitely see Fermat follow this convention in his work, although not immediately. So sorry. All right, here's Pierre de Fermat, the lawyer, judge, part-time mathematician, who's a famous guy. So, all right, fine. Let's see some of Fermat's work. Fermat's working, I could write this. I don't know if you can even see this. You can probably zoom in on it in some way. But in any case, Fermat's working about the middle of the 17th century. We are definitely making our way towards modern time as we go forward, as we always would. All right, so here are two famous results of Fermat. Okay. So the first one is down. Oh, oh, the first one is second. Well, that's interesting. I think we should do the little theorem first. So fine. So notice Fermat is, like I said, he's a busy man. He's busy being a lawyer and a judge and all these things. So often you will see him say things like, I would send you the proof if I were not afraid to be too long. So he doesn't often prove things, and that's just the way, I guess. So he says here, every prime number is always a factor of one of the powers of any progression minus one. Progression here means one of the powers of any progression. I think that just means any number. I don't think that is really scary as a progression. So every prime number, I'll write this, maybe I will switch to this and show you it, is a factor or divides one of the powers of any progression minus one. So I'll use A for the any and N for the power minus one. Okay, and the exponent of this power is a divisor of the prime number minus one. So the exponent divides the prime number minus one. Okay, fine. And after one has found the first power that satisfies this proposition, all those powers of which the exponents are multiple of the exponent of the first power also satisfy this proposition. So P also divides any number times that exponent. I will let you see this larger. There we go. This is what's called Fermat's little theorem, or I think in this book it's called the lesser theorem. This is a true theorem. Fermat probably did have a proof of this one, which is noteworthy because many of the things he says he can prove, he probably couldn't. But he probably did have a proof of this result. And this is something that shows up a lot in number theory and algebra. And it's just the kind of things that he was working on at the time. Let's see if we go back to his, there we go. Thanks. So the more famous Fermat statement is here when he's reading some Diophantus work about dividing a given square number into two squares. He says, oh, well, all right, I'm intrigued about this dividing a square number into two squares. That should remind you of the Pythagorean theorem, but Fermat's next step should not. By the way, please don't be reminded of the Pythagorean theorem when thinking about Fermat's last theorem. He says, in contrast, it's impossible to divide a cube into two cubes or a fourth power into two fourth powers, or in general, any power beyond the square into powers of the same degree. Of this, I have discovered a very wonderful demonstration. The margin is too narrow to contain it. This is, again, Fermat's excuse. He may have thought that he had proven this, but given what happens in history afterwards, there's no way that Fermat actually had a proof of this result. He is claiming, by the way, that there's no x cubed plus y cubed equals z cubed for positive integers, x, y, and z. There's also no x to the fourth, y to the fourth, z to the fourth for positive integers, x, y, and z. This is a big, important claim. Well, I don't know how much it's important, but it's big. Lots of people work on this for lots of time to come. And this gets lots of attention. We will talk about this often over the next few weeks. We will often come back to Fermat's last theorem. Like I said, it is highly doubtful that Fermat proved the whole thing. It's mostly doubtful that he proved any of it. Maybe he proved the case n equals 3. That's would have been within the range of what he knew and what he could have talked about. All right, so that's Fermat's last theorem, which we will talk about a lot in the weeks to come. All right. Fermat did something else. He did lots of things. He was busy for being busy. He did a lot of mathematics for being a busy man when he wasn't doing mathematics. One thing he did was introduce coordinates in a way very close to the way that we use them. So he talks about this connection between geometric objects and their equations. And that's a big deal. It's an important deal. This connection between geometric objects and their equations is a way to connect geometry and algebra, which historically have seemed to be two very, very different mathematical disciplines, to put them together into one. All right, so here is some work of Fermat making sense of just an equation of a line. So he starts off, and I'm kind of wanting, I can almost do this. He starts off wanting to look at this picture and this text. So let NZM be a straight line, be given in a particular position. NZM, I think you see here, is what you would call the x-axis. It's the horizontal axis. And what he's trying to do is to find the equation of line NI. Notice eventually he will say, hence NI is given in position, and it's easy to make the synthesis. So he is trying to describe the line NI. Notice in so doing, so do pay careful attention here, as I said above. Fermat is using Viet's convention that when he's talking about quantities, not points, don't confuse points and quantities. When he's talking about quantities, consonants are constant. Maybe that's a good way to remember that. Vowels are variable. Maybe that's a good way to remember that also. I don't know if Fermat or if Viet wanted to use that, because I quite honestly don't know the words for any of those four things in French or Latin, but it's nice in English. All right, so what he says is we have some known quantities, D and B. Those are fixed quantities because they're consonants. And when D times A is equal to B times E, the point I will describe a straight line that is this straight line. So that's really his idea. This is a straight line through the origin. We're presuming N is the origin in his coordinate system. And so I guess we can come up here. What we have is D times A equals B times E. Remember, A and E are our variables. You would like to call them X and Y because that's what you like calling variables. Viet and Fermat like calling them A and E. And the other two are constants. So because of that, we really just have a proportional relationship, which gives us a straight line. Okay. Fermat gives us another example of a straight line, of a different straight line. This time he's looking at straight line, here's my pointer, MI. And this is discussed down here. So let Z plane, so something two-dimensional. Remember, just like Viet, Fermat is careful about keeping his dimensions straight. So if it's going to be something subtracted from something two-dimensional, B times A, this needs to be something two-dimensional for Fermat. So let Z plane minus D times A equal B times E. Notice we were fine with the subtraction symbol. We don't have a symbol for times yet. Interesting. Let Z plane minus Z times A equal B times E. And Fermat's a little uncomfortable with the fact that this has had to be two-dimensional. So why don't we let Z plane be D times R. So now he has two factors there. then we will find that B is to D as R minus A is to E. Let me write this for you a little bit. So we have Z plane minus dA equals B times E. And he said that Z plane was R times D. And then he knows that he can factor out a D and get R minus A equal B times E. And he says this is a great equation for this new line. Notice what we have here is something very similar. It's still a linear equation. If you put x and y here, you'd be happy and recognize that, and it wouldn't disturb you, I do imagine. All right. The next thing he talks about, he says we omit a great number of other propositions in typical Fermat being busy and not doing everything style. The second thing he talks about is A times E is Z planar, in which case we get a hyperbola. This should sound familiar. We've seen this before. I'm not going to go through much about the hyperbola because we have seen it before. So when you have your two variables multiply together to equal a constant product, we get a hyperbola. And like I said, we've seen that before. So I'm not going to talk more about it. All right. We'll talk about one more of these before we move on, because we do have lots and lots and lots of other things to do. All right, the next thing that he has here is if BQ minus AQ is to EQ in a given ratio, then the point I, that is the point, what is the point I? It's the point with coordinates A, E. Remember, you would say X, Y. Fermat says AE. So I is the point with coordinates AE. But actually, I said a while ago that points aren't variable, but now I think I take back my statements. I think it's not an accident that he's using point I to be the moving point. So I take that back. Point I is a point that is intentionally chosen to be a vowel because it is also variable. All the others are changing, N and M and Z and so forth. All right. But what's he talking about here? BQ minus AQ equals EQ. Why does he have all those Q's? Q's are not variables there. Those are lowercase q's. They're short for square. So what he really has here, and yeah, I think I will turn this off for now, is B square minus A square is to E square according to some ratio. So we could say as P is to R, but what we really want is that, all right, B squared minus A squared over E squared is equal to some constant. This is a constant that Fermat actually never names, so I'm going to call it P, just because I was using P's over there. And notice, if we work with this a tiny bit and not much, we get B squared minus A squared equals P times E squared. Fermat gives a different explanation for this because his standard way to describe an ellipse is a little different from the ones that you're comfortable with. But if we think the way we would, we could then put this equal to B squared equals A squared plus PE squared, and then divide the whole thing by B squared. And then we would get 1 over here. And we could even break this into 2 pieces. And now, at least I hope you have seen enough ellipses in your mathematical career to recognize that this is a standard form for an ellipse. All right, good. So there's some of Fermat. We will see a little bit more. But we also have much to do, so we won't see a lot more. We will see some of his work on area, not in much detail. Fermat did find area under some curves, which is nice. He surely didn't write them or call them integrals, but he was finding area under curves, and it doesn't matter whether you call them integrals or not. They are. If you're finding the area under a curve, you are finding an integral, even if you don't call it that. It is worth noting, one of the things that was unusual about his work, and by the way, this is similar work in Roberval, who we will see some more of soon. One of the things that's unusual about this work is he did break them into rectangles, which should look familiar, but he broke them into rectangles of varying widths. He made them longer and longer the further he went out, which is different from the way we would do integration. One of the things that's characteristic of Fermat's work in area is that he devised different methods for each of the problems, not a unifying method for all of them. I am attempting to load and thankfully talking while it's happening. This is Roberval's work. Roberval, among other things, found some areas inside of spirals and broke them up into sectors, which should look like polar coordinate areas. He also found the area under a cycloid. Here's a graph of a cycloid. The cycloid is the path that a point on a circle moves as the circle rolls along a line. So here we have a circle. If we roll this circle along this line, the point comes down because that's what happens when you roll things. And if you roll it this way, the point goes this way. So this curve, this middle curve, is the cycloid. I would hope you would have seen that in your calculus classes somewhere, but if you haven't, there it is. So Roberval finds the area under that curve. All right, let's go back. And here's Mersenne. And I will write a couple things about Mersenne and Fermat. And then we'll talk about Pascal and Fermat. Everything's Fermat-centered in one way or another today. And that's kind of the way. Fermat was someone who talked to a lot of different mathematicians because it was something he was interested in. So regarding Mersenne and Fermat, they are most known for a conversation they had concerning prime numbers. And Mersenne said that numbers of this form are often prime. And Fermat said that numbers of this form are always prime. Fermat wasn't right. Mersenne wasn't quite right either, because Mersenne said these ones are, and some of them he was wrong about. But both of them were right to say that numbers of these forms are often prime. If we take 2 cubed minus 1, we get 8 minus 1 is 7. That's prime. Okay, fine. And Fermat, in his case, if we take a number that I can manage doing here, if n is 3, I would have 2 to the 8th, which is 512, plus 1 is 513. And I think 513 is prime. Actually, it must be, given what I know about Fermat primes. Primes of this form are called Fermat primes. They are related to compass and straight edge constructions of regular polygons. We'll come back to that story in 100 years or so, 150 years. Mersenne primes are related to perfect numbers, as Suzuki tells you about. you might not have known what perfect numbers were before, so I should say a little bit more about that. If this number is prime, then 2 to the n minus 1 times 2 to the whole n minus 1 is perfect. Let's see an example of this. So when n equals 3, I said this number is prime, and that's true. So for n equals 3, we get 2 squared times 2 cubed minus 1. This is 7. This is 4. This is 28. And what does it mean to be perfect? 28 equals the sum of all of its factors. This is an idea that goes back to Euclid. The factors of 28 are 1, 2, 4, 7, 14. Oh, not all of its factors. All of its factors except itself. Otherwise, that would be impossible. And do notice that 1 and 2 and 7 is 10, and 4 and 14 is 18, and we do have 28. So whenever this number is prime, and then that's what Mersenne was exploring, is when is this number prime? Whenever this number is prime, then this number is perfect in that meaning. All right, great. Let's go back. So there was Mersenne. Ta-da. I'll show you Pascal before talking about the problem of points. So there's Pascal. Also a relatively famous guy as far as things go. Maybe more famous for philosophy or religion things than for mathematics things, but definitely did a lot of mathematics things also. Let's first talk about Pascal's connection to Fermat, and then I will move forward and talk about stuff that Pascal worked on without Fermat. Amazingly, people were allowed to do mathematics in France without consulting Fermat. Seems hard to imagine sometimes. All right, I think Suzuki did a very bad job of describing the problem of points. I think that this website does a much better job. So I'm going to use it as something to talk about, mostly so that I don't have to write everything, which would just take a lot of time. So 2 players play a game of chance, fine, with the agreement that each player puts up equal stakes. So they both put some money in to begin with. And the first player wins a certain number of rounds will collect the entire stakes. Suppose the game is interrupted before either player is won. How do they divide the stakes fairly? So here is a particular example that illustrates how Fermat and Pascal thought about the problem of points. And this is noteworthy because this is, as I hope you're recognizing, we have not talked about probability. This is definitely early days of an interesting problem in probability. Okay. So in this very simple situation, unlike Suzuki's silly example, here we go. We have 2 players. They're playing a series of points. Maybe you can imagine they're just flipping a coin heads and tails over and over again. And the first person to get 4 heads wins. That's the game. It's kind of a silly game, but that's the game. And they have equal probability of winning each time. So one, or maybe even better, probably not the first person to get heads, but one picks heads, one picks tails. And the first person to get 4 of their things wins. All right, so the problem is then, suppose that player A has won 2 points and player B has won 1 point. And then they're like, oh, we gotta go. Well, what should we do? We have this money, how should we divide it? And that's the story here. So what we're going to do is we're going to pretend that they could continue playing the game, see what the options are, and see how we should divide things. All right. So far, A has 2 points, B has 1 point. Because A has 2 points and B has 1 point, this says A needs 2 points and B needs 3 points. it's going to take at most 4 rounds to finish this game. If we played 5 more rounds, they'd both have 4 points, and we don't need that. We assume that we will actually play these 4 rounds, even if we don't need them, which is an interesting way to handle this situation. So the game might be over, but we're going to write out all possibilities. This is what Fermat says. He says, let's write out all the possibilities of playing 4 points. This was the approach of Fermat. Of course it was. There are 16 such. These are the different things that could happen. All right, great. Those are fine, 16 things that could happen. And I don't know what S and F stand for, but it's a success and failure that player A wins the point. Fine. They could have just been A's and B's. That's probably would have been more clear. But in any case, so remember, player A needs 2 more to win. So any of these where player A gets 2 more, they will win. And so 2, 2, 2, 2. So some of them have more than 2. Yeah, that's fine. This one they only had 1, 3, 2, 2. This one they only had 1. This one they only had 1. This one they only, all right, fine. So of the ways the game could continue, in 11 of them, player A wins. So, all right, and there's 16 total ways. So the probability of player A winning is 11 out of 16. So we should, when we stop the game, we should give player A 11/16 of the stakes. They said that the stakes was 64. So we take 11/16 of 64, which is really just 11 times 4, which is 44. So that's how Fermat did this. And Pascal said, well, that's great, but we shouldn't have to list out all the possibilities. That's a bit tedious. He knows the possibility that each of the possibilities is 1/2 to the 4th. And he knows a thing or two about binomial coefficients since he's Pascal and he does all this work on the triangle. Okay, so Pascal says, we really just need to find the number of, out of 4 remaining trials, the number of ways that 2 or more are A winning. So he finds that and adds the 4 choose 2, 4 choose 3, and 4 choose 1, which is 4 choose 4, which is just 1. And he gets 11/16. And he said, we could do this and it would be shorter, especially if we have the arithmetic triangle hanging around. So that's some of the ideas of the problem of points. And I hope that's a little more clear than, and I really did not mean to do that. I hope that's a little more clear than Suzuki's explanation of that was. I felt he was kind of weak. All right. Did I look at Pascal? Yes, I did. I remember how he looked. So Pascal did actually do a lot of work with the arithmetic triangle. It's not that he didn't. And he deserves some credit for that. No denying it. Here's what the arithmetic triangle looked like to Pascal. Again, different. It's interesting. Of the different versions we've seen of the arithmetic triangle, the one that looks most like the way you're used to seeing it, I think, is the one we saw first of Yanhui's arithmetic triangle. At least that has the orientation that I'm used to seeing. But okay, that's fine. He has numbers here that should look familiar for all the entries, the numbers. There's also a whole lot of variables. He has different variables in the different boxes so that he can refer to them in the text. This makes reading this somewhat difficult, but okay. So the consequences of Pascal that he found in the triangle are, let's say, hard to read. So they're written here. and you can sort through them. If you're going to sort through them, here is a translation. It's not even a very nice translation, I don't think. I don't know why they're called PKL. I guess because Pascal refers them to rank L and rank K. But Pascal, unlike the way we would do things modernly, starts with 1 and 1 instead of 0 and 0. So this is ugly. This is not Pascal's formula, by the way. He didn't quite have it in that form. All right. Okay. And there's some things here. I think I'm going to write them in modern notation up on the board instead. All right. By the way, I haven't given many dates since Fermat, but the point is they're all working around the same time. All these people were talking to Fermat, they were all working at the same time. So Pascal has 19 consequences of the triangle, 19 results that he proves about it. 1 and 2, or 2 and 3, we have seen before. These were the consequences we saw from Munim. This is what we would now write as n choose k equals n minus 1 choose k minus 1 plus n minus 2 choose k minus 2 plus all the way down to n minus r plus or minus 1 choose 0 whenever that happens. All right, so that's just that pattern that we saw in Munim where you go up and then take a turn. And you might ask, why are these two different ones? Because you can either do this way or that way, and Pascal noted them as two different things. All right, fine. I think in the list as I was perusing them, and this is my personal taste, perhaps you feel differently, I think the fourth one is the most interesting and the most unfamiliar to me. So apparently n choose k minus 1 is equal to the double sum, which is the sum of all of the binomial coefficients before that one. All right, that's interesting. I didn't know that one. That one I have not seen before. And that is an interesting consequence. I think I will give Pascal the most credit for that one. The fifth one is the unsurprising n choose k equals n choose n minus k. I am rather convinced that every single person who we've seen talking about this triangle before noticed that. It was pretty obvious. That's just the symmetries in the rows, and I don't think anyone was surprised by that. This is not 6, it's 8. The 8th consequence that Pascal noticed is that the rows sum to 2 to the n. And I kind of think that most people recognize that. I think that didn't surprise anyone. I think that is reasonable, that the work we've seen before, that the people would have seen that result and not been surprised by it. Consequence number 12 is interesting. It's close to something that we saw from Levi Ben Gershon. Remember, as I mentioned with his work, that Levi Ben Gershon was not widely read. And so many people pick on this result and say that this is the first instance of induction in mathematics. Pascal does prove this by something that is an inductive argument. There's no denying that. It's a very similar result to what Ben Gershon was proving using permutations. These are combinations, not permutations. So it's a little bit different, but it's the same idea. The results after this one were, to my taste, rather boring. Things about how this row relates to the next row, which is rather clear given this. I didn't find them as interesting as this one. I think is very interesting. These are familiar, and then there's other things that are kind of dull. But okay, that's one of the things Pascal worked on. Let's see what I want to do. Not that, this. All right, we have done a lot today. Thank you for hanging on as I fly through things. And we will end where I want to, which is nice. All right, Pascal also has this theorem on conics. That's a geometric result. This is interesting. It's different. It's where geometry starts to go. Geometry is an interesting subject because there's a serious question of when you think about the kind of things that the ancient Greeks did in geometry, what comes after that? It's things like this result. And the best way to see this result is not to look at the original source, but is to look at this animation that I will show you after it loads up. All right, here it is. Great, that loaded up pretty quickly. Let's make it bigger because why not? There we go, it's as big as it can be and still fit on the screen. All right, so this is a result that's true for any conic section. It's drawn here on a circle, all right? So you could do the same thing on a parabola, on an ellipse, on a hyperbola. It's just I happen to have the animation for a circle. All right, what we say is, now hold on, because this is where geometry goes these days, and it's a little bit of a different thing than what you're used to thinking about. It says, pick a point on the circle. Connect it, actually, there's a better idea. Pick 6 points on the circle. Do that. Connect them in a cycle. What do I mean by that? Start at one, connect it to another, to another, to another, to another, to another, until you come back to the beginning. So pick 6 points and connect them in a cycle that way. All right? Now, look at those 6 edges. There's 1, 2, 3, 4, 5, 6 edges here. Look at the edges that are 3 apart in the cycle and see where they intersect. So 1, 2, 3, 4. 1 and 4 are 3 apart, so that's one of our intersections. I said 1, 2, 3, 4, 5. That's 2 and 5. That's our second intersection. And this is 3 and 6. That's our third intersection. Yeah, this is what happens in geometry in the 17th century. When you do that, no matter where the points are, the intersection is always 3 points, or the 3 intersection points are always on a straight line, which is this red line, which is why it's red. The nice thing about this particular software is we can play with this. Okay, good. But one thing that's noteworthy here, so notice as I do this, yeah, they always do stay in a straight line. That's good. The order of the points doesn't matter, which is why I said that. We can go cycle through the points however we want. So I can bring this point over there. And when Suzuki talked about this, he called this Pascal's hexagon theorem. There we go. We can eventually make this look like a hexagon. If we shuffle the points enough so that the edges, I see where they go. This point comes there. There's our hexagon. Now we have a problem that these two sides are parallel, so we don't want them to be parallel because then they don't intersect, or maybe we're starting to deal with projective geometry in which they intersect somewhere in a mythical place. But now it's hard to see. So if we bring it down, okay, so now we have a hexagon and we can actually see the intersection. Sometimes it goes off the screen, that's understandable. But this is the flavor that geometry is having in this point in history. Geometry is a curious subject because it was so heavily emphasized at the beginning. And then there was this feeling like, well, they did it all. So maybe if I bring, there I can see all three intersection points. But this is what geometry starts to look like at this time in history. That is Pascal's results on conics. Remember, any 6 points, you can cycle through however you want, find the 3 apart intersections and so forth. Remember also, this is not just circles, but any conic section. You can do the same thing on a hyperbola, on a parabola, on an ellipse. It all works out just fine. That is our beginning of chapter 7. And as you know, mathematics is getting significant and involved in modern. And we will have lots more involved modern mathematics for you next time. Thank you for hanging on with us. I look forward to hearing from you. You have an exam that I don't know if you've done it before or after you watch this video. I imagine there's some in each case. Take care. I look forward to reading your writing. Bye.